All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are gonna continue. Uh, we're gonna continue learning about PWM stuff. I've made a massive breakthrough for the past, I don't know, 3 days now, maybe. Um, I don't remember how long it's been. It's been a couple of days. I've been trying to solve this issue. I've been trying to figure out this PWM related issue that was making it so our code wouldn't work. Um, just a second. Here. Okay. So after doing a bunch of research yesterday, through Gemini, I realized that even though and this might have just been because there were way too many variables, involved, and I just kind of got confused. But um, I there was a lot that I was missing. So it really helps to go back to the low level, and like I did research on. So in my research, I continued digging deeper. The first thing I realized was the main issue that I was having was that uh, because of the resolution that I'd set, setting a very low frequency, setting a very low frequency was causing an issue, because there's two places where we can run into problems. One is setting the duty resolution. That's the number of ticks that um, one period should contain. And so that's one place where you can have an issue. And the other is if the divider that's being used to divide your higher frequency signal, if that divider happens to be bigger than what can fit into the divider register, then also you'll run into an issue. And the reason I didn't realize that that's what was happening was because I wasn't being given any errors. There's no errors being reported back. And so when I fed this into Gemini, Gemini explained that you have a 6-bit resolution, and you have set your, oh, wait, we are dropping frames. Right at the beginning of the stream, we are dropping frames. Give me a second while this stabilizes. Let me also open up my stream on my phone, so I can have the chat open, and then we can continue. Okay, good. The connection is stabilized. Let me switch to my chat, and we are good. Right. So, um, yeah, dude, I'm super excited because I managed to get this working. Not only did I manage to get it working, I also understood exactly why I was running into the issues that I was running into. And it comes down to basically a mismatch of. So, okay, at the beginning, when we were learning about PWM, I remember reading somewhere in, I think it was in the Impel Rust book, within these tutorial pages. I remember I think in fact um it might have been on this page itself. Actually, okay, it might have been on this page. It could also have been in the was it in the fade method or the configure? No, it might have been in these pages. So we had discovered that we have a couple of these variables, right? We have resolution bits. So this is essentially the resolution of your duty cycle. Sorry, the resolution of your period. So each period is going to be that long. Then you have your source clock, which is in our case it's APB clock, and that's an 80 megahertz signal. It's an 80 megahertz frequency clock signal. Then you have your PWM frequency. That's the desired PWM frequency. That's the frequency that you want. You want a PWM signal to be created at. And then you have the clock divider. the clock divider, it took me a very long time to understand exactly what the clock divider is doing. But it turns out that the clock divider is literally just dividing the signal down, because we have a very high speed signal, right? Our source clock is 80 megahertz. That's 80 million ticks per second. We don't want our PWM to be that high. We want it to be much lower. So to make it much lower and bring it down to the desired uh, PWM frequency, we use a clock divider. And the clock divider gets calculated based on a certain formula. I think the formula was basically um, I was doing it yesterday here. So the clock divider um, formula is our APB clock. I still have the variable. Yeah. So it's our APB clock divided by the the desired frequency, let's say 5 hertz, multiplied by the duty resolution. So in our case, let's say we want to give it 10 bits. Okay. Let's do this. So that is our clock divider. And then the clock divider gets used to divide down the 80 megahertz signal. And it's really interesting because after understanding this, I truly understood what this specific image is showing. What this image is showing is that this is our signal, right? This is, I'm assuming this is the 80 megahertz signal, and the clock divider makes it so every um, every set number of ticks, it counts one tick, and that one tick is going to be used in the counter in our PWM hardware. So we have a counter that basically just counts the number of ticks, and those ticks are what we use to determine that yeah, we have finished one cycle. So if our duty resolution, or let's say our duty resolution, if our resolution is set to 6 bits, if our resolution is set to 6 bits, what we are expecting is for each period to have 6 bits worth. That's 64. So here, oh, there. So each period is going to have 64 ticks, and after 64 ticks are complete, we move on to the next cycle. Now, the interesting thing here is we use the divider to essentially divide down this massive signal. And that's something really interesting to me, because this divider is then what's each of these upticks that you see here in the signal. Each of these upticks is what gets fed into the counter and gets counted as one tick. So you can see it mentions here output clock pulses. So this gets fed into the counter, and that's what's being counted as our tick. And then as soon as we reach to, you know, whatever the duty percentage is, whatever the duty cycle is, then the signal gets set down. So this counter is what's being used to output. This counter is what's being used essentially as a clock signal to output our PWM signal. And the PWM signal starts out high, and then once you hit your duty percentage, then it goes to low. But keep in mind, the ESP32 has no notion of time. It's using the ESP32 has it doesn't have an understanding of time. In this case, it's just using this clock signal, the 80 megahertz clock signal, in order to create the notion of time. So we have 80 megahertz. In order to divide this, so if it's 80 megahertz, that's 80 million ticks per second. And since it's 1 second, so we divide 1 by 80 million, and that gives us whatever, decimal number that is. um, how do I, okay, so let's say this divided by APB, um, APB clock. So that's our number. Let me convert this to a string. And then, is there a format? Yeah, let's print this. We're going to print this as this. And here we're going to do dot 10f. I hope I've done this right. I have not done this right. So I need to put this dot 10f in here. Let me do this. Yeah, this is our number. This is how many seconds each tick is. And if we convert this, so this is currently 12.5 nanoseconds. Right now it's being displayed in seconds because we did, 1 divided by 80 million. This is how long one tick is. And this is how we give the ESP32 some notion of time. This is how we create the notion of time. And I find that incredibly interesting. We studied this at the beginning when we were learning about ESP32 clock signals and stuff. And I feel like I hadn't fully wrapped my head around the concept of the divider and exactly how the signal was being divided down. Like, what did the signal look like after it was divided down? And like, what was happening? How exactly is the signal being divided down and then used? And now that I understand that, there's a divider and there's a counter and stuff, the interesting thing is, okay, this this thing about counter was actually taught at the very beginning here in PWM resolution. It was somewhere in here. Let me read out this whole thing. So, timer operation. The timer plays a key role in the PWM generator. It counts from 0 to the specified maximum value stored in the register and then resets the cycle over. This counting process determines the duration of one complete cycle called the period. Compare value. The timer's hardware compares its count. Why was I reading this? Oh, yeah. This I was trying to explain that this is basically do our how we generate the pulse. This is how the time is being counted. You can see these discrete steps. Give me a second. My mouse is misbehaving a little bit. Do I need to change the battery like right now, or which battery is this? I probably don't have batteries. Okay, that is not a good thing. I think we're good. I think we're good for now. So, this counter is essentially what this counter counts. Um, this counter's count is what determines when we have completed one entire period. And okay, so we have our resolution bits register. We get to set whatever the width of it is supposed to be. It can be anything from, I think, 1 bit is a thing. I don't know if 1 bit is a thing, but it can be a certain number of bits up to 20 bits. So you can have up to a 20-bit register. I believe that's our counter. That's our counter. The counter register is it can be up to 20 bits, and 20 bits is a lot because that'll give you a lot of very discrete steps. Like, that's 20 bits. So we would be able to divide one period into, what is that, 1,048,576 steps. If we went for the full 20-bit thing, we would be able to divide it down into that many steps. And in this diagram, you can see um, a 4-bit resolution. So we have 16 discrete steps for each period. Okay, now The interesting thing here is that we have our resolution bits. We have our counter register, which is a 20-bit register. I'm actually wait. Let me come back here. Does it also mention in the in this diagram? Yeah, it mentions here as well. Counter 20-bit and fractional divider 18-bit. So our counter is 20-bit. Our fractional divider is 18-bit. However, 10 bits is all we get out of those 18 bits because sorry, within the fractional divider register, 10 bits is all we get. So that's also why it mentions here, somewhere here, the division factor ranges from 1 to 1023. So if we do 1 and do this, there we go, 1024. So because it's I was about to say because it counts from 0, but that's not what's happening here. Either way, 1023. So we only get 10 bits out of that 18-bit register, meaning our divisor can only be this. It can only be anything within this value. So earlier, when I had come up with that divider, I think that divider would also give us an error. Let me test that out real quick. I'm going to set this is ls. We need to go to hs. So I'm going to do 10 bits and then I'm going to set, what are you doing here? Yeah. Then I'm going to set this to 5, wrong thing, 5 hertz and save this. And if I've done this right, then that means I've done this wrong. And it should, yeah. Let this upload now, and we'll know that my logic is correct here if it doesn't work. That's a weird thing to say, but yeah, I'll fix it. I'll fix it like once we test it. That's weird. Uh, it is on, but it's not blinking. So it's not supposed to like it's not supposed to be blinking. I'm surprised that the thing is on at all. In reality, let me show you what it's supposed to be doing. I was expecting it to not turn on at all, but it turned on. In reality, it's supposed to be doing this. Let me upload this, and you should see it blinking now. I might need to work on a tool of some sorts. There we go. This is what I've been trying to do for the past 2 days, I guess. And like a lot of yesterday's stream was about this as well, I believe. All this is doing, if we go back to the code, there's nothing going on in the loop function. Everything is commented out. There's these two variables that are just not doing anything. There's literally nothing going on. All we've done is configured the channel based on our timer. We all we've done is call the configure method on the channel, and it just starts outputting this signal. So now we have a constant 5 hertz signal, and let's calculate our divider value based on what we've provided here. Okay, so I've provided a 20-bit um, signal. So okay, I think previously when I was looking at 20-bit, I was thinking that, oh, maybe this is going to be like the max that the register can hold. However, our duty resolution could be lower than this. That was my way of looking at it. But I think in reality, what's happening is that it is setting the entire duty resolution for one period to be exactly that. So 20 bits means we are setting it to uh, where was that value? 1 million something something something. So let's try that. Let's plug in our formula. Let's say APB clock divided by, and I haven't done. I'm okay. I haven't done this since yesterday. Like I haven't done this at all. Like just now I tried plugging in a new thing and testing out the value. So let's see how this works or how well this works out. 15. That is our divider. There's the fractional portion as well, and that goes into the remaining 8 bits in the register. So we get 10 bits. 10 bits is again this. Man, having a Python interpreter open is such a good idea because I have like a straight up a calculator open here. I don't I don't need to I don't need to worry too much about, having to run like a Python script or anything like that. This is so helpful. But yeah, so this is our divider. 15 is our divider. 15.25 something something something. Um, let's try using this formula. Okay, let's try. Wait, so the formula was given here. FPWM equals our APB clock divided by clock divider multiplied by 2 to the power resolution bits. Let's do that. Let's calculate our APB clock equals, wait, do I have math.log? I do. Okay. Uh, actually, that's not what I need though. I probably need math.power. That is a built-in function. Wait, I didn't need this? I needed this. I needed this. Yeah, okay. I needed to import math. Okay, power of, I don't know. I don't know what the variables are here. Oh, x and y. So x to the power of y. Okay. Right. So that would be 2 to the power of 20, which is that. All right. So to calculate our PWM, we are going to do um, APB clock divided by clock divider, which is 15 point. I don't know how precise I should be. Should I round this off maybe? I'm not sure. Let's give it this value and then let Python decide what it wants to do. And then here we do math dot power 2 to the power 20 5. There you go. So it's not exactly 5. I need to figure out what that very tiny fractional that is a tiny fractional portion. So let's call it 5. Let's call it 5 hertz. So now we have our holy shit, I'm so excited, dude. Now we have our logic down. Now we have the math down. I understand all of this properly. Now I even understand um, what was going on in this portion of the diagram, in the H timer portion. So it takes, in our case, so far, I haven't managed to get a ref tick. Um, I haven't managed to get a ref tick clock source. At some point later, I'll have to look into how to set up a ref tick clock source. For now, we only have APB clock as our clock source, which means we're going to assume 80 megahertz for the entire time, right? That signal gets fed into the fractional divider. I should look into the so from the fractional divider, our signal is getting fed into the counter, right? But then in the fractional divider, I need to look into how exactly things are working because Zainar, hello, hello, welcome to the stream. Yes, the light is blinking, and the amazing thing is that we are doing this by hold on. Here, the only thing we are doing here is that we have configured the high-speed channel. This is being done through PWM, pulse width modulation. We are not doing this using the LED on-off toggles. Or, well, we are not doing this by calling the LED toggle function and using time-based methods. I'm just passing a 5 hertz PWM frequency with a duty percentage of 50%. So each pulse is half on and half off. So half of the pulse's duration will be on and the other half will be off, and then we'll have five such pulses throughout the second. That's why we see a blinking kind of thing going on here. I wanna. I think I can get away with 1 hertz. Yeah, I think I can get away with 1 hertz because if I plug the where's our thing here? Okay, I should make this a function. 76, yeah, that's our divider. That's gonna fit in, and yeah, there it is. So this is literally PWM. This is only PWM. This is not. We are not toggling the GPIO pin on or off. We have just configured PWM on one of the pins, and then we are playing around with the timer and the channel. And see, this is where I'm kind of glad that I took the time to look deeper into this, even though at the time I didn't understand this diagram very well. And even now, I only understand the left side of it. I haven't looked too much into the right side of it because I was more focused on the timing of the thing. Because, like, okay, we have 80 million ticks, right? 80 million ticks. If we divide that into, so we have APB clock. Um, what is our divider? Our divider is 15.2578 something something something. Wait, let me do this. Okay, so for 5 hertz, let's say CLK div equals this, and then we would just be dividing it by that amount, isn't it? Like I'm assuming that's how our so every that many ticks, we've set a resolution of 20 bits. We've set a resolution of 20 bits, so PWM has to be that long. But then the the divider also determines, like, the divider determines. Oh, the divider determines. See, this is where the understanding the math becomes important. The divider is what determines what gets counted as one count in our counter. The divider is what determines that, because the divider is telling us that, okay, every n number of pulses, one pulse is considered one count. So every n number of pulses, it allows one pulse to go through, and that one pulse goes through into the counter and increments the counter. And the counter is set up so that so it's a 20-bit counter. If we use a 20-bit resolution, it's going to let the counter go up to 1,040 something thousand something something, and once it hits the max value there, it's going to reset the counter. um what was I saying? I was trying to understand this. Okay, so clock div, right? So then we are trying to divide, um, it should be 80 million, right? But the thing is, no. Oh, yeah, yeah, no, no, no. Yeah, it should be 80 million. So we are trying to divide this. I'm trying to, okay, I've I've always had this issue in terms of vocabulary, math vocabulary, specifically when we are saying, like, okay, subtracting so and so from so and so versus saying so and so minus so and so. Because if we are saying we are subtracting b from a, that would be kind of like this, right? But then that same thing can be said as a minus b. So similarly for division as well, I've always had this issue of, like, um, dividing a into b, or is it a divided by b? Like, there I always have like a confusion, but then I have to just like visualize it. Like, okay, we are dividing um we are dividing a, which, let's give it 20 into four pieces, which would give us five. So that's one way that I can look at it and remember that the vocabulary is supposed to be, so and so. Um, what was I? Oh, yeah, I was trying to divide the 80 million into these many. So every okay, that's our divider, right? There has to be something that tells the divider when it's supposed to let a signal through. What does that circuit look like? I Google basic stuff all the time, never been fantastic at remembering things. Yeah, unless I try to like understand something, I'm just not going to be able to use the thing, and I hate having to remember stuff. I mean, to a certain extent you have to kind of remember, but like I would prefer to understand whatever it is that I'm remembering, because it makes it easier for me to remember that, because then it's not like, oh, this is just how it is and that's how things are. It's more like, this is why we are doing it in this way, and that's why you have to do it in this way. Um, so my what I'm assuming here is that, right, let's say APB clock temporarily, let's say our I would I kind of want to make this kind of a diagram using something like, well, not this curly bracket kind of thing, not this specifically, not even the text. I want to make this up down kind of thing in Python. Like, I need something very simple in matplotlib that lets me do this. Let me just Google this with Gemini. Also, by the way, guys, holy shit. Okay, if you guys are on social media, okay, cyber decks they're becoming somewhat of a pop culture phenomenon now. They're they're let's say they're the trending tech thing that people are doing. And the amazing thing is that even people who are not that tech savvy, even they are interested in cyber decks. Granted, for them, it's less about actually it's for them it's less about the technical side of things and more about building an aesthetically pleasing computer. So a lot of people are getting a Raspberry Pi and getting some sort of a Raspberry Pi compatible LCD or screen or something, and then they're setting up a power supply. And because it's a Raspberry Pi, so you can connect, keyboard and mouse and a bunch of other things. However, and I didn't know jack shit. Oh, give me a second. While I'm speaking about this, I'm just going to freeze the RTMP feed temporarily so things can cool down a little bit. Now, what was I saying? I think I was saying that I don't know jack shit about what do you call it? Um Cyberdex. I didn't know anything about Cyberdex. I knew so less about it that I was assuming that for something to be a cyber deck, it has to have like computing capabilities. But it turns out, no, that's not the case at all. I was having a conversation with Gemini about this to understand the whole culture surrounding it. And that's what gave me hope, because I don't have the money to buy Raspberry Pis. I wish Raspberry Pis were cheaper. It's not like they're expensive, they are cheap. They're about as cheap as they can get. But I don't have that kind of money either. I do have the money for, ESP32s and display modules and stuff like that. So in the amount of money that I would be spending on one Raspberry Pi, I could get a couple of microcontrollers, a couple of display modules, a couple of peripherals, and various other types of modules and stuff within the price of one Raspberry Pi. So I would prefer to do that. But yeah, I asked Gemini. I'm just gonna read out the conversation like directly. Okay. because this is really interesting to me. And I, because of cyberdecks, because of the culture around, or how should I say, because of the concept of cyberdecks, I'm getting ideas for stuff that I want to do with my own DIY projects. Okay, so this is what I asked. Actually, there was another conversation that I was having with Gemini about where was it? Was it I think it was this one. So I asked Gemini, I said, does a cyber deck necessarily have to have a keyboard and mouse input? Or are there various types? Would the others even count as cyber decks? Is it it's a cultural thing, isn't it? And then Gemini replied with, you've hit on a fascinating intersection of science fiction trope and DIY subculture. The short answer is no, it doesn't strictly need a keyboard and mouse, but the definition gets blurrier the further you move away from them. Technically, a cyberdeck is a cultural construct born from born from 1980s cyberpunk literature, specifically William Gibson's Neuromancer. This is actually making me curious for any William Gibson or Neuromancer based like movies that might have been made. I need to look into that, because if this is from literature, then what does the movie adaptation of that look like? Okay, all right. Continuing what Gemini said. So Gemini was like, okay, what actually defines a cyber deck? In the real world maker community, a cyber deck is generally defined by intent rather than a specific input method. To be a quote unquote deck, it usually needs portability. So it's not a desktop, it's meant to be used in the field. It needs aesthetics. It usually looks high tech, low life, rugged, customized, or salvaged. So you could either build your own kind of thing, or you could salvage, which is also something a lot of people are getting into now, because the idea of cyber decks, it gave um, it gave people, how do I say this? It didn't give rise to the idea of solar punk. It gave, because cyberdecks are a cyberpunk. They're a cyberpunk thing. They belong to that genre, right? However, there is another genre called solar punk, which is essentially a mixture of cyberpunk and eco friendliness. So you're trying to create high tech stuff, but in a very environment friendly manner. So you're using a lot more greener, quote unquote, greener technology. You're salvaging as much as you can, recycling as much as you can. Older hardware, instead of constantly manufacturing newer hardware, you're using older hardware, repurposing older hardware to do a lot of tech stuff. And that kind of falls in line with like what I would prefer to be doing. I mean, I'm granted, in my case, I'm not doing it because I'm trying to be solar punk. In my case, I'm doing it because I would prefer to try and repurpose older hardware than buy newer hardware, because I find it more interesting to try and, hack older hardware and see what I can do with it. But yeah, it's super interesting to me that the rise of cyber decks is it's opening up that conversation. It's starting that conversation about, hey, how can we also be solar punk, not just be cyberpunk? How can we start reusing discarded electronics? Okay, so continuing, the three things that Gemini was saying, it usually needs portability, meaning it's not a desktop, it's something that you can move around in the field. And aesthetics, yeah, it has to be rugged or customized or even salvaged. So you're using like older electronics or older things that are meant to be discarded, and you're repurposing them. And then specialization. It's often built for a specific task like hacking, radio monitoring, terminal access, etc., rather than being a general purpose laptop. Okay, alternative input types. If you ditch the keyboard and mouse, you're moving into the realm of specialized decks. Here are a few that definitely still count. You have neural links, the pure cyber deck. In fiction, a deck doesn't have a screen or a keyboard, it has a neural interface that plugs directly into your brain. If we achieve high fidelity brain computer interface, that would be the truest form of a cyber deck. Okay, so that's one option. That's not an option right now for us, but that's being developed. That's also not to be fair. That's not what I was going for, anyways. What I was going for was more along the lines of a very simplified input interface. So maybe it would be something simple like a hex keypad that is then connected to a device and it can be used to type into things. I also got this other idea where I was like, okay, what if I applied the idea of terminals to like terminals from back in the day? Because okay, for those of you who don't know, the idea of terminals, like we say terminal window um for this kind of where is it? Here. We say terminal window for this kind of thing, where we get a shell. We have this terminal window. Within this terminal window, there's a shell provided. We can type in commands, and it's gonna execute those commands. Uh, right. Give that a second. Oh God, what just happened? Oh, okay, okay. That's interesting. Yeah, I enabled a shortcut somewhere here. Let me open up my Western, let's say config, Western.lua. What does it do with the queue that I accidentally threw in there? Oh, that's what it does. It opens up a second buffer. That, that's what it does. Um, oh, I just realized that you guys cannot see any of this because I turned off the RTMP stream. I'm going to turn that back on and refresh this feed so that you guys can see it. Right. Let me refresh this. Um, give me just a second because something seems to be stuck here. And I need to close this real quick. I'm just gonna, is it this one? It's this one. Yeah. So I'm just gonna end this. Okay, great. Awesome. There. Cool. So what I was doing was this time without the queue. So in here, I believe I have configured something to show. Um, we have tab navigator, we have this, and did I not configure this? I guess, I guess not. Well, okay, what I was going to show was that I had configured because I thought I'd configured the um, there's a specific Sorry, I'm a little distracted here because okay, that's what it was. So I'm just gonna show it over here. That's interesting. Why is it not showing up here? Hold on, guys. I'm confused about this. I need to check elsewhere because I'm trying to reproduce something that I just did, but I'm not able to reproduce it. And I can't remember what specific setting I had enabled in order to allow this. So basically it's just like an emoji menu. That's all it is. It's nothing more. And it is accessible through I guess here I could open up, but you guys are not going to be able to see that. Show it I'll have to show it here. Um Emoji. Yeah, it's Shift Control U. I don't know if it's going to show up here though. Yeah, this is it. Is it capturing? I can't tell. Oh yeah, it's capturing. Yeah, this is the menu basically. That's it. That's the menu. It just wasn't popping up here for some reason. Yeah, I'm not sure why it's not popping up in the smaller ones. It I was able to get it to show previously elsewhere. I think I did show it, didn't I? Yeah, dude. I don't know. I got it to display once. For some reason, it's not displaying properly here, but it was displaying before. Either way, I can use it to do this kind of stuff. Now, why was I talking about this? Oh, yeah, back to the thing I was mentioning. So, usually when we think about a terminal, we think about this kind of thing, right? This window where we get a shell and we enter commands, and those commands are executed. But the idea behind terminals, like if we go way back, like decades ago, it turns out terminals were their own separate devices because computers back then, and they were like much more massive, much more expensive as well. Um, they were fast for their time. They're definitely, nothing compared to what we have today. But for that time, they were incredibly fast. But they didn't have like these dedicated screens that we have these days. These days we have computers that we can connect monitors to. Back then, what you had was a massive computer, and you would have a terminal that you could bring and connect to this computer. And the only function of this terminal was to allow you as the user to give input through some kind of keyboard, or maybe they had some other input device at the time. Um, and so you give input through that, and you receive input through you receive output through it as well. Usually it would be some either either a screen displaying something, or maybe sound or something like that. So that was the whole point of that was the whole um, concept of terminals. These were devices that didn't really have too much processing power, but they had the ability to give input to something else and receive input from something else and display that input as well. And so these devices were then connected to bigger computers, and that's how people would do computations through these computers. They used these terminals, but then over time, tech improved, and we didn't necessarily require a separate terminal to communicate with a computer, to communicate with a machine. Why was I even explaining all this? I think I was trying to say that in terms of building like a cyber deck kind of thing, a cyber deck, the idea of cyber deck has it's kind of inspired me to build a lot of my tech as as essentially computers that I can connect a terminal into and control in that way. That's what I was trying to explain. That this has given me the idea to build a terminal, my own terminal. I'll have words. Holy shit! I'll have to see how I want to go about setting up my own terminal. But a lot of the stuff that I'm building, I would definitely like to um, make it interfaceable with a terminal. So that way, I'm just building these devices. I'm not adding buttons into them so that people can give input. Instead, I have my own dedicated terminal that I'm gonna hook into the device, either wired or wireless. I'm still exploring that as well, because I'm looking for low power options. I'm not looking for something that's going to drink a lot of power. Well, I mean, my own terminal, I don't mind if it drinks a lot of power, but then the other devices, the devices that I'm hooking into, I would prefer for them to maintain their power consumption the way that I built them to, maintain. Give me a second here. Yeah, okay. So, uh, yeah, dude, I'm excited. I'm excited to do cyberdeck stuff. I was thinking that I'm not going to be able to get into the idea of cyberdeck, but then now after having this conversation with Gemini, I'm actually inspired to do a lot more cyberdeck stuff. None of my cyberdeck stuff is going to include Raspberry Pis, or even OSs for that matter. If anything, I'm going to be building my own software stack in order to be able to, use a cyber deck. But that should be interesting. Like, I'll build my own thing that I can then load up onto various other devices. So I can code in the ability to be interfaceable. That should be something interesting. And maybe I can build like my own um, maybe I could do something like how we have ESP HAL that interfaces with, not interfaces with, but like it implements the embedded HAL. Similarly, I could make something that is, interfaceable or cyber deckable, for lack of a better term. Something that can be interfaced. Like, I can create an interface that um, a bunch of my other devices can implement, because all of this is going to be done using Rust. So like that's a massive advantage. Holy shit, dude. I'm gonna have a lot of fun with this. This is gonna be a fun bunch of projects, not one project. Okay, going back to like the input types. Um, Gemini mentioned, okay, one is the neural links. The other is the slab or tablet deck. Many modern builds use high resolution touchscreens. While it looks like a rugged tablet, if it has external antennas, a custom mechanical chassis, and runs a pen testing suite, the community still classifies it as a cyber deck. Then the third one is haptic and wearable inputs. Corded keyboards. This is actually the first time I've heard of corded keyboards. I don't know if that just means wired or if that's like a glove sort of keyboard. Let me look into that. Hold on. Let me Google this real quick. Words. Let me Google this real quick. What is going on? Holy shit. Corded keyboards. Okay. Okay. These seem to be keyboards that fit your they fit the shape of your hand. So mainly you're supposed to be they're like single hand kind of keyboards. That's actually not a bad idea. Yeah, that's not a bad idea. So it's not a full-on keyboard. I mean, it could be, but like it's not necessarily always a full-on keyboard. It's a keyboard with like a limited set of keys for specific purposes, and it may have like dials and stuff on it as well. Um, I don't know if I'm getting the exact definition of it right, because while I am seeing keyboards with a limited number of keys, I'm also seeing like full-on keyboards which have extra stuff attached to them, and even that's being called a corded keyboard. So I guess I'll have to look at the definition of corded keyboards, but this should be interesting to get into. Yeah, yeah, this should be interesting to get into. Also, speaking of keys, I feel like I could look into trying to get keyboard connectors, or like the key connectors specifically, like the key mechanism. I could look into getting something like that as well. I'm sure I can get like, you know, um, something with a chip already, and the mechanical parts and everything is built, and I just need to slot it into something and then connect it to my microcontroller, and I can, you know, use it in whatever way I want. Um, but yeah, yeah. Let me go back to the conversation here. Okay, corded keyboards. Next, we have VR and AR inputs. All right, okay, and then we also have the other type. The next type of cyber deck is hardware only decks. Some decks are built solely for physical manipulation. Think of a deck covered in toggles, sliders, and patch cables, like a modular synthesizer used for signal processing or radio frequency manipulation. So apparently that can be called a cyber deck as well. Okay, then I was like, okay, is this a cultural thing? Gemini responded saying, yes, absolutely. If you take a modern iPad and put it in a Pelican case, is it a cyber deck? Most enthusiasts would say no. Why? Because the cyber deck is an expression, oh, sorry, a cyber deck is an expression of technological sovereignty. It's about building a tool that the manufacturer didn't intend for you to have. And then Gemini quoted, the street finds its own uses for things. That was said by William Gibson, apparently. Okay, whether it uses a keyboard, a trackball, or a neural shunt, it counts as a cyber deck if it embodies the spirit of customized, portable, and slightly rebellious computing. If you were okay, then Gemini ended the message with asking a question. I'm assuming just to get me to keep talking. But yeah, yeah. That has been that's what I've been busy with. I asked further questions as well in terms of like, communicating with systems and stuff like that. Um, And I'm excited. I cannot state this enough. I am excited to get into building cyberdecks and building cyberdecks for various purposes. Because like my cyberdecks are not going to be um, full on computers, or the idea with my cyberdeck is not to have an entire laptop that I can carry around. The idea with my cyberdecks will be, being able to control various things. Still a cyber deck though, so that's cool. Initially I was very hung up on the definition of cyber deck, and like if I build all of these things, would they really classify as cyber decks? Turns out, yeah, yeah, there's a lot of things that can classify as a cyber deck. All right, now getting back to what we are doing here. This, yes. Okay, right. So we were doing this calculation, right? So we have a number which is 5,242,880. And this raised the question for me that what exactly is the divider doing? Like I understand conceptually the divider's job is to divide the signal, and every set number of ticks, it counts one tick and sends that tick to the counter. But where where is that operation happening? Wait, I feel like I need to conserve memory here because I feel like my system is about to get overloaded. Well, the other system. Okay, did that open up? Yes, it did. Okay, what was my question? Oh, yeah. I'm doing ESP32 studies. I'm currently trying to understand how PWM hardware works. Specifically, I'm trying to understand what happens when the APB clock signal goes into the um, divider. I understand that the divider more or less, well, basically divides this signal such that um, every set number of ticks, one tick is sent to the counter. But I don't understand what hardware is doing that. And I also don't know where in the TRM I would find this info. Um, I'm aware that the clock div register is 18 bits, but I'm not sure where and how the actual division is happening. I'd imagine, okay, so I've sent the prompt, Gemini is going to answer now, but I'd imagine there's like a comparator involved. Actually, wait, there was a comparator involved here as well, right? Though, if so, okay, if we look at this diagram, our tick signal, it comes from here, it goes into the fractional divider. My assumption is that it gets divided here, and every like within this divider we have circuitry that is only going to let one tick every few ticks get through. So every few ticks, only one tick gets through, and that one tick gets counted by the counter. And just like this, we have, every few ticks, one tick gets let through, and the counter increments and keeps incrementing until the duty resolution, until the target value, whatever our duty resolution is, until that is reached. And then once that is reached, the counter goes back to zero, and we basically have moved to the next pulse, or the next pulse, next period. Okay, all right. Gemini responded saying, it sounds like you're diving deep into the ESP32 technical reference manual, which is the only way to truly master this hardware. You know what? Yeah, I agree. And even though a couple of days ago I was saying that maybe I shouldn't be going too deep into this, like speaking about the LEDC, the LED PWM controller, even though a couple of days ago I was kind of questioning whether I should be going this deep into it. Now I'm glad that I did go this deep into it, because now I actually understand what I'm looking at, and I would have had to go this deep anyways in order to understand PWM. At least, in a way that I am satisfied with. Give me a second here. Okay. All right. So, carrying on with what Gemini said, um, where was I? Okay, to answer your first question, in the ESP32 TRM, you should look at the LEDC and PWM, sorry, LEDC or MCPWM chapters, specifically the architecture and register summary sections. The LEDC divider is often described as a fractional divider, which is where things get interesting. Has the divider been mentioned somewhere here, like how it's working? Maybe it has been mentioned and I just missed it. Yeah, maybe it's in this. Yeah, maybe it's mentioned and I just missed it. Okay, all right. Specifically, architecture and register summary. Um, is there an architecture section? There is architecture. Okay. And then there's register summary, which is down here. But this is just all the registers. Okay, all right. Wait, what is this? Output signal diagram? A fading duty cycle. Okay, back to what Gemini was saying. Oh yeah, this is where it gets interesting. The hardware, how the division happens. In digital hardware, a clock divider isn't just a gate that stays closed. It's typically implemented using a digital phase accumulator or a counter-based comparator. The integer part, the counter, the most basic part of the divider is a dedicated down counter or comparator. If your divider is set to n, the hardware takes the high-speed APB clock. An internal register counts APB clock cycles. When the count reaches n, a single tick is issued to the PWM counter, and the internal divider register resets to zero. Oh. So internally in the fractional counter, in the fractional divider, that's what it's called. Yeah. In the fractional divider, also, we have a counter that's constantly counting um, the number of ticks that have passed, and its target value is basically whatever we have decided the fractional divider to be. Okay, okay, all right. Okay, now I'm getting it. Then the fractional part. Since the ESP32 LEDC divider is 18 bits, it includes an 8-bit fractional part, 10.8 or 14.4 format, depending on the version. Um, so since it uses an 8-bit fractional part, it can't just count to a fixed number. To achieve a frequency like divide by 10.5, the hardware uses a sigma delta modulator or a dithering technique. It can't actually pulse halfway through a clock cycle. Instead, it alternates the integer division. To get 10.5, it will divide by 10 for one cycle and 11 for the next cycle. Over time, the average frequency is exactly what you requested. That's interesting. Okay, okay, all right. Okay, what the hardware looks like inside. Think of the divider as a gatekeeper circuit. The input is APB clock and the value from your 18-bit register. The logic, a series of flip-flops forming a prescaler. The output is a narrow pulse, um, also called strobe, apparently, that acts as the enabled signal for the PWM for the main PWM counter. The main PWM counter doesn't quote unquote run on the divided clock. Did I say run? Um, the divider basically sends a signal so and so so and so so and so. I don't understand how. Okay, whatever. I don't know. Maybe I said run. Maybe Gemini is just trying to say like in case I think it's running. Whatever. Where? Yeah. Okay. The main PWM counter doesn't run, quote unquote, run on the divided clock. It runs on the APB clock, but only increments when the divider logic gives it the green light pulse. That's an interesting way to look at it. It's still running on the APB clock signal, but it's only incrementing whenever the divider tells it to increment. So technically, then yeah, it is running off of the divider only, unless it's doing something else later on with that APB clock 80 megahertz signal. Unless that's the case, yeah. So all of this is essentially still running. That's wild, dude. Because now the dots are starting to connect in my head that, yeah, all of this is running off of that main clock source signal. It's just that as we divide it down, we are telling later on hardware, like hardware that's later on down the line, we are telling it when exactly it's supposed to count, when exactly it's supposed to consider, you know, one tick has happened. And that's kind of crazy to me. Wait, okay. So am I getting this right? The fractional divider also has a counter, but in that case, the the counter max value is being decided by the divider uh, value or division factor. Yeah, let's say division factor. The division factor, and every time um, the divider hits that max value, it sends a pulse to the counter, to the PWM counter, which then counts one tick. Exactly. You've got the core logic perfectly. The quote unquote max value of the divider's internal counter is effectively your division factor. To be precise, the hardware doesn't actually quote unquote slow down the clock wires. It chooses which pulses of the high speed clock. This helps. This definitely helps. Yeah, this line definitely helps. To be precise, the hardware doesn't actually slow down the clock wires. It just chooses which pulses of the high speed clock or our APB clock are allowed to count. The pulse swallow mechanism. That's okay. Okay. In digital logic, this is often called clock enable strategy. I've seen clock enable mentioned in some other hardware. I've seen clock enable mentioned in some other hardware. Is that how they count the pulses? Is that how they count the ticks? Holy shit, dude. It's starting to click now. Oh my god, dude. I'm getting this. I'm understanding this PWM shit, dude. We're making progress here. We're making lots more progress. Unfortunately, I don't have too much remaining time today, but we are going to continue making progress tomorrow. Let me finish reading this though. Um, okay, the mechanism. In digital logic, this is often called clock enabled strategy. The internal divider counter, this is a hidden counter inside the PWM peripheral that it increments on every APB clock cycle. The comparator, the hardware constantly um, the hard holy shit the hardware constantly compares this internal counter to your division factor register. I should look into how we do the fractional portion, even though it was just explained, but like I'm still curious about like how we are doing the fractional portion, like what exactly is going on there. If we are just doing counters here in integers, then like what's going on with that fractional portion? Okay, the hardware generate. Wait, what's the next? The trigger. The trigger. When internal counter is equal to division factor, the hardware generates a single pulse or a tick, a single cycle pulse or a tick. This pulse acts as the enabled signal for the actual PWM counter, the one that determines your duty cycle. Okay, this acts as a counter for the PWM counter that this acts as an enabled signal for the actual PWM counter. This was actually, wait, if we go back here, I'm glad that I have all of these tabs open. But yeah, if we come here, right. So this is our count. Um, this is our count. This pulse acts as an enable signal for the actual PWM counter, the one that determines your duty cycle. Okay, okay. The internal divider counter resets to 0 and starts over. Awesome. That's after the trigger. How the fractional part changes the max value. This is where it gets clever. Since a digital counter can only count whole numbers, you can't count to 10.5. The hardware uses a fractional divider, often a first order sigma delta modulator. If you're if you set your divider to 10.5, the hardware quote unquote cheats by changing the max value of the internal counter dynamically. In cycle 1, the divider counts to 10 and then sends a pulse, and in cycle 2, it counts to 11 and then sends a pulse. I should sit down and like write out those pulses to understand like or to be able to visualize how that's working. Okay, the result. Over two cycles, you've had 21 APB clock ticks and two PWM pulses. 21 divided by 2 is 10.5. Oh, 21 because 10 and 11. And that looks like 10.5. That's interesting, dude. That's wild. That is crazy. Holy shit. Okay. Okay. All right. You know what? Awesome. Okay. So, give me a second here. Okay. I think let me see if I'm able to get this going. Um, yes. Okay. So, yeah, that's gonna be it for today's stream. I'm raiding into someone called Nettle Root. They are studying for something. And yeah, that's going to be it for today's stream. We made some good progress today. I'm excited about my understanding. So excited about this whole research that I've been doing that yesterday I didn't do anything Western related, any research Western related, anything analog electronics related. I just remained with this so I could properly understand it because I feel like doing the research off stream, it helped me understand this a lot better. Um, yeah, it just helped me understand things a lot better. But yeah, that's going to be it for today's stream. Zainer, thank you very much for stopping by and hanging out. Anyone else who might have been lurking in the stream, thanks for hanging out. But yeah, dude, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.